Okay, welcome everyone to Zach seminar. It's my great pleasure to introduce Adrian Langer from University of Warsaw. I know Adrian for many years. First time we met was in 1995 or 1994 in Eger, Hungary, and almost 30 years ago. And Adrian will talk today about Chern classes of vector bundles.
Okay, thanks a lot. That's really great pleasure to talk here. I mean, it would be better if it were not online, but live, but one cannot have everything. So I will talk about Chern classes, and most of my talk is going to be very general. So I will talk about basic results, about some kind of restrictions on Chern classes one can get for mostly projective varieties, but we will also see some restrictions on quasi-projective varieties. So the first definition I would like to recall is the definition of semi-stable sheaf. So for that, you need to fix a smooth projective variety and some ample divisor or a hyperplane section. And then one defines a slope of sheaf. I will always assume that this is coherent and torsion-free. So you can really think about vector bundles. So sometimes it will be more convenient to think about vector bundles. And then the definition of the slope is that it is just the degree of this coherent sheaf with respect to this ample hyperplane section divided by the rank. So here, the degree is just the intersection of the first Chern class with h to power dimension of x minus 1. So if you have a hyperplane section, it's just the degree on a general curve. And then the definition is that sheaf is slope semi-stable with respect to this particular polarization if for every subsheaf the slope of the subsheaf is at most the slope of the sheaf you started with. And so this is this definition appeared a very long time ago, first in the case of curves in Mumford's work, and then in many other places, as we will see a little bit. So instead of this kind of definition, one can also do that in more general way when I replace this ample divisor with a collection of ample divisor or even of Neff divisors, so limits of ample divisors. So I simply take the collection and then I compute the degree with respect to this collection intersecting the first Chern class with intersection of all these divisors. The most important in my talk is the inequality that was proven by Bogomolov in 70s. So he proved that if you have a smooth complex projective surface and a slope semi-stable vector bundle, then the degree of this discriminant that is defined below is greater or equal than 0. So the discriminant is just 2 times the rank, which R stands for the rank of E, times the second Chern class minus this R minus 1, the first Chern class squared. And I always think about this as a class in the char group of codimension 2 cycles on this variety, and then this integral is simply the degree of this. Well, here it is the degree of the zero cycle. So it really makes sense. And then one can characterize these slope semi-stable vector bundles for which the degree of the discriminant is 0. Namely, if we have something, well, for simplicity, okay. If we have something that is slope semi-stable with respect to whatever polarization, then there exists a finite covering and a line bundle such that the pullback twisted by this dual of this line bundle has a filtration with stable vector bundles with vanishing Chern classes, and these occur to correspond to flat unitary vector bundles. And well, so this kind of characterization goes back to the work of Narasim Seshadri in the curve case, then Donaldson, Uhlenbeck, Yao in higher dimensions, and well, also Simpson and Demay, Peternel, Schneider. So there are many people one could put here to this kind of characterization. And there are more general versions of this, really, and I will talk about this a little bit later. So this is what happens in the surface case. But we can try to cut down to the surface case if we have something higher dimensional, and that there is a theorem of Mehta and Ramanathan, which says that if we have something that is slope semi-stable and we take a general hyperplane section of very, very large degree, then the restriction to this general divisor is slope semi-stable with respect to the restriction of this ample polarization. And once we have this one, then it is completely obvious that if we are over complex numbers, then if we have something slope semi-stable, then the degree of the class that is obtained by cutting down the discriminant to the surface is non-negative. So this has some applications I will tell a little bit later on, but well, this, as I said, this is going to be pretty general talk. So let me go to some generalizations to this of this result in case of complex projective varieties. So if we have smooth complex projective variety, then one can consider Higgs bundle. So this is just a pair consisting of, say, a vector bundle E together with O of X linear map from this E to the twist of E by the cotangent bundle. And this should satisfy some condition that is called, say, integrability, which means that theta wedge theta is equal to 0. So this really means that this E has a structure of a module over the symmetric algebra of the tangent bundle of our variety X. And when we have this, then, well, first of all, there is a result due to Hitchin and in the curve case, and then Simpson in general, which says that every stable Higgs bundle. So now stability is defined in the same way as before, except that we consider only subshifts that are preserved by this Higgs field. So when every stable Higgs bundle has a Hermitian Young-Mills metric, so there is an analogous result in case of usual stable bundles. And then this was used by Simpson to show that if we have a semi-stable, actually he proved this in the stable Higgs bundle case, but there is not so large difference. If we have a semi-stable Higgs bundle, then we still have the same inequality for the Chern classes. And there are also some versions of this. Well, one can think about versions of this in positive characteristics. So it is easy to say that this is not true. Even the usual Bogomolov's inequality fails if you have a variety defined over a field of positive characteristic. So we try to consider this positive characteristic case in the smooth projective case. And then, as I said, in general, it's not true, but if you assume that your variety is liftable modulo, say p squared, then we have essentially the same inequality. So if we have a semi-stable Higgs bundle and the rank of this Higgs bundle is at most equal to the characteristic, then the discriminant has non-negative degree with respect to this ample polarization. And this, well, once we have this result, then the resulting characteristic 0 follows immediately by spreading out. So this really implies the previous inequality. and this gives an algebraic proof. So I'm not going to talk much more about that, except that one can still generalize this. So in the case of logarithmic Higgs bundles, so instead of just taking the usual Higgs bundle, we take a simple normal crossing divisor D and then consider vector bundle together with this logarithmic Higgs field. And if this is semi-stable of rank at most equal to the characteristic, then the degree of the discriminant is still greater or equal than 0. So the funny thing is that this result in the characteristic 0 version, it was proven also by Mochizuki in 2006, but characteristic 0 version requires really lots of work, because the point is that one wants to generalize this result of Hitchin and Simpson on existence of this Hermitian Young-Mills matrix, and this becomes much more difficult in the logarithmic case in characteristic 0, whereas the proof in that I gave in the logarithmic case and in the usual, it's essentially the same. There is not so much difference between these. And this has some applications to varieties in positive characteristics, similar to the applications that one gets in characteristic 0. So, for example, if we have a smooth projective surface with non-negative Kodaira dimension, then there is well-known Miyaoka-Yau inequality in case of surfaces in characteristic 0. But it fails in case of positive characteristics. So we still need to assume that this is liftable. And then, first of all, there was a result going in this direction due to Shepard-Baron in '89, who proved this in characteristic 2. So if we have a smooth projective surface in characteristic 2, which is liftable modulo 4, then 4 times the degree of the second Chern class of varieties of this surface is greater than C1 squared. So this is worse than this Miyaoka-Yau, and Miyaoka-Yau starts to work in positive characteristics starting with characteristic 3. And then it is really the usual Miyaoka-Yau inequality. So 3 times the degree of C2 is greater than the degree of C1 squared. And obviously, this implies the inequality in the characteristic 0 case. So these are just some applications of this kind of result, but it has many other that I'm not going to talk about. Instead of that, I'm going to talk about something different. Really, well, the main problem that I would like to or the question that I would like to ask is whether this Bogomolov's inequality is only an inequality. So we have something that is slope semi-stable with respect to some polarization, whatever. We consider the discriminant, which we know is a class in codimension 2 cycles in the Chow group. And if you have, say, smooth variety, and then we can ask several questions. First of all, is this class an effective cycle? So it is, well, this would be certainly much stronger than the usual Bogomolov's inequality. We simply know that the degree is greater than 0, but we don't know anything about this being effective, and in general, degree 0's, well, non-negative degree cycles can be really, really bad. So even the degree 0 cycles don't need to be represented by classes of effective cycles. So this might be a little bit too much, and maybe we should ask a question in the after tensoring with rational numbers. So we forget about possible torsion and still ask whether this is a class of an effective cycle here. And if we manage to do that, then we can try to ask these kind of questions for semi-stable Higgs bundles and and possibly in positive characteristics. So there are some questions that one can start asking after that, but the two basic are the first and the second. So the first one, well, in the surface case, things are kind of easy sometimes. So if we have it's easy to see that if you have a smooth projective variety over an algebraically closed field and zero-dimensional cycles that has strictly positive degree, then its class is effective in the group of zero-dimensional cycles in this Chow group. And then obviously this implies that if we have something that is slope semi-stable on a smooth complex projective surface, then if we know that the degree is greater than 0, then the discriminant is effective in this in the codimension 2 cycles on the surface. So you see that we are left with the case where this degree of the discriminant is equal to 0, and we already saw that this is somehow connected to flat vector bundles on our variety. So, so unfortunately, this doesn't work, this effectivity in case of where the degrees of this discriminant is equal to 0, and there are some easy examples over complex numbers. So even if we take an abelian surface and a line bundle in peak 0, one can do that in such a way that self-intersection of this line bundle is non-torsion in this Chow group of 0 cycles. Then if we take a direct sum of this line bundle with its dual, then it is completely obvious that it is slope semi-stable with respect to every polarization. But the discriminant is equal to minus L squared, and the degree of this is 0, but unfortunately it's not a class of an effective cycle due to this non-torsion. So so you see, it's not so easy to see what to do with this, but maybe we somehow asked the wrong question. Well, here we have slope semi-stability. In case of stability, maybe things improve, which maybe one can hope for, but not so much, because if we have, say, a stable rank 2 vector bundle, which after a finite covering becomes slope semi-stable of this kind of form that we see here, then we can't expect again the discriminant to be effective. But this is the only thing that prevents us from effectivity. So this is what I'm going to study next. But before that, I'm going to go to a slightly different topic. So, so I'm going to talk about the conjecture of Bloch, which is a conjecture on flat vector bundles, on Chern classes of flat vector bundles on smooth complex projective varieties. So the conjecture says that these Chern classes should somehow live in the lowest possible stratum of the Bloch-Beilinson filtration on the Chow group on this of codimension I cycles. Well, the problem with this kind of formulation is that we don't really know what this means, because there is no, I mean, this Bloch-Beilinson filtration exists only conjecturally, and therefore this conjecture depends on another conjecture. But we can hope that, I mean, one can see that this conjecture implies the fact that these classes are torsion in the groups of codimension I cycles modulo algebraic equivalence. So we don't take it modulo rational equivalence, but when we take it modulo algebraic equivalence, then this conjecture predicts that these classes are torsion there. So, I mean, actually, I still used some standard conjectures to apart from the block, apart from the existence of a block Bailing filtration, one needs to have standard conjectures to actually deduce this second part of the conjecture. So I will say that the second part is a weak block conjecture and the first one is strong. Strong doesn't make much sense, weak makes perfect sense always. So now, well, there is a theorem proving what one can possibly prove I mean, the conjecture depended on some conjectural things, but if we look at the Lin's cohomology, when this conjecture was proven by Reznikov, so he in '95, so he proved that these Chern classes really are torsion in the Lin's cohomology. And then one can leave them to the classes in H2i minus 1 with x c divided by zi, and then these lifted classes are also torsions. That's what he proved. So there are some results going in that direction, but this blocks conjecture somehow is.
Adrian, it doesn't make much sense here when you look at the Chern class of E. It's not defined in the Simodzik homology, it's just defined in the Lin homology.
Yes, I know. I said that one can define the classes which live in this H2i minus 1. I agree that this is not a good notation. Okay. So forget about the first part. The second is what I want. Okay, so so this is one of the conjectures. Another conjecture that one has around is the block-Bailinson conjecture, which says that if we have a smooth projective complex variety, but if we assume that this is defined over a number field instead, then the cycle class maps map from the tau group to with the Lin's cohomology, all these cycle class maps are injective. Okay, so this is something that you see together with this Reznikov result that we have here says something interesting in case of smooth projective varieties defined over number fields, namely that the Chern classes are of flat bundles are still torsion in tau groups here, if we have a variety defined over a number field. But let's see what happens in general. So in general, I proved the result that is somehow depends on this block-Bailinson conjecture in the rank 2 case. So it's in the E. Okay, so the result is the following. So we have a family of flat vector bundles on, say, smooth projective variety X, which is parameterized by some irreducible variety. And now if we assume that at some point or complex point of this S, the geometric monodromy group of this flat vector bundle contains SL2C, and if we assume that the block-Bailinson conjecture holds, then the discriminants of these vector bundles at every point of S are torsion, and the torsion, the order of torsion is bounded independently of the point. So here, okay, so I should make a few comments. So what is the geometric monodromy group of a flat vector bundle? We simply look at the associated, say, topological monodromy group, and which is a representation of topological fundamental group in GL2C, and we take Zariski closure of the image of this one. So this is the geometric monodromy group, and then I assume that this contains a L2C at some point, and then what this says is that the order of torsion is bounded everywhere, which is kind of strange if you think about this a little bit, because this example that I gave earlier could also be thought as an example of a flat unitary connection, rank 2 connection, but then this discriminant in this case was not torsion. But here, if we assume something about the monodromy groups, then it becomes torsion. So there are a few comments that I would like to make. First of all, these geometric monodromy groups, they behave very badly in families. So they can jump a lot in an unpredictable way. In particular, they are not algebraically constructible in families. So this assumes something about one point that this monodromy group is large, but at other points it can be small. Then one can formulate this theorem in case of quasi-projective varieties, but then I would need to talk about families of flat vector bundles with regular singularities, and I wanted to avoid that. But the result is essentially the same. And then if you have projective varieties, then one can also prove a higher rank version of this theorem, except that this time we look, say, at Chern classes, at some Chern classes in, say, in the codimension, that live in codimension R char group. So, so here a comment maybe is the following. You see that this result says that n times the discriminant is equal to 0, but it doesn't really mean that, say, n times the second Chern class of this Vs is equal to 0. So actually it is easy to see that second Chern class do not need to be torsion. It's really the discriminant, something that is independent of the twist by a line bundle, that is torsion. Okay, so now I want to go a little bit to the positive characteristic case and see what happens then. So here, if we have something that is defined over algebraically closed of positive characteristic, and we have smooth projective variety, and we have strongly sloped semi-stable vector bundle, which means that all the Frobenius pullbacks of this E are slope semi-stable, then if we assume that the degrees of the first and second Chern character vanish, then the Chern classes of this vector bundle are torsion in this group of algebraics of cycles modulo algebraic equivalence. And the proof of this is rather easy once one have some results. So, so the proof is that we simply look at all the Frobenius pullbacks of our vector bundle. This family, under our assumptions on the first and second Chern character, is bounded. And then the fact that this is a bounded family means that there exists some constants m and m prime such that these Frobenius pullbacks by m times and m prime times are in the same flat family of vector bundles. So in this BI, the difference of these Chern classes is 0, but this is really equal to p2 power m minus p2 power m primes times this ci. So we see that these ci's have to be torsion. So this is an easy argument here. And then one can prove also something different. So the previous result was about strongly semi-stable vector bundles, but they are not so well behaved when you say try to prove something in characteristic 0. Because if you have something slope semi-stable in characteristic 0, then it is not known whether it stays strongly slope semi-stable in any characteristic. So instead of that, and if one wants to deal with Higgs bundles, one can prove the following result. So if we have a smooth projective variety which is liftable modulo p squared, and if we have a slope semi-stable Higgs bundle, one can also do the logarithmic case without any troubles. If we assume that the degree of the discriminant is equal to 0, then one can show that higher Chern classes of this vector bundle are proportional to the first Chern class to the appropriate power. And in particular, this means that the discriminant is torsion in B2 in codimension 2. Wait. Yes. Yeah. So here all these equalities are in BIX tensored with Q, and here if you take I equal to 2, then this means exactly that the discriminant is torsion in B2. And in general, you have some conditions. So in particular, if you assume that the first Chern class vanishes and the second Chern class vanishes, then you know that all the Chern classes are torsion. Okay, so this can be also reformulated for slope semi-stable vector bundles with connections or with logarithmic connections, and the result is still the same. And then, okay, so the proof is very similar to the previous proof, except that one needs to use the Higgs theorem flows. So this is some gadget that was introduced by Lanschenk and Zuo, and I also proved. So they really introduced this stuff, but then they had a conjecture that this should exist for all semi-stable things, and then we proved this independently using somewhat different methods. And then when you use this and use boundedness of semi-stable vector bundles with fixed first and second Chern class, then the proof is essentially the same. So now, as I said, we want to get some results in characteristic 0 using positive characteristic. In case of inequalities, this was not a problem. But now the problem is much worse. So because one cannot detect whether a class in the char group is torsion just by passing to reductions modulo some prime numbers. For example, here if we have a non-torsion line bundle in peak 0, then all its interactions are always torsion because they are line bundles defined on a variety which is defined over a finite field. But obviously this L is not its class in the rational char group is non-zero. So this cannot be done in this way, but maybe one can do it a little bit in a little bit different way. Namely, we don't really need this in this case. What we need is something somewhat weaker. So the question is the following: if we take a class in codimension I char group and assume that for almost all the primes, the reductions of this class are torsion, then we can ask whether this class still lives in this lowest stratum of the Bloch-Beilinson conjecture. Bloch-Beilinson filtration. So this would if we had this, then this would immediately imply Bloch's conjecture using this result that I told you about, characteristic P. And then if we knew that that under these assumptions, this class is torsion in this group of cycles modulo algebraic equivalence, then this would prove this weak Bloch's conjecture. But I have no idea how to prove any of these, or whether these are expected or not. It's difficult to find any counter examples to this. The first one would be, say, curves in threefolds. And then there are some things one could try to, some cycles that could produce counterexamples, but I didn't try to prove that, and it's tempting to think that it is still fine. Okay, so a very optimistic conjecture about Chern classes of say flat vector bundles on smooth complex projective surfaces would be that for every smooth projective surface, if we assume that for every smooth projective surface, the pullback is still of our bundle is still slope stable, when say the discriminant is torsion. And I mean, this is just the conjecture that I formulated in the surface case for simplicity, but one can easily go to higher dimensions and to higher Chern classes. I just wanted to state it in this simplest case. And I formulated in case of any algebraically closed field, which is kind of funny, because when you look at the algebraic closure of a finite field, then one can easily prove this this result, this conjecture. So what one really wants is to prove this in the case of complex numbers, and then I really don't know what happens. So one can somehow reformulate this in the sense that if you have a flat vector bundle with simple geometric monodromic group, then Chern classes are torsion in these showering groups. And the result that I mentioned earlier about rank 2 case was a kind of this result, except that it was done also in the families. So so the rank 2 is now somewhat pretty well understood, but the higher rank is much more delicate, and I don't really know counterexamples of this in the higher rank case. Okay, so so now I would like to go to a somewhat different topic. We cannot see what happens with the discriminant so well in case of vector bundles, but if we take the push forward of the discriminant by a flat projective morphism of relative dimension 1, then from the codimension 2 cycle, we produce codimension 1 cycle. So now we need to deal with line bundles, and they are much easier to deal with somehow than. So we could try to get some results in this relative case. And the first result along these lines was proven by Molivaki, who proved relative version of Bogomolov's inequality. And this relative version says that if we have a flat projective morphism of relative dimension 1 and between smooth complex quasi-projective varieties, and if we have a vector bundle on X, and if we assume that this vector bundle is semi-stable for some fiber, well, in some sense, if a fiber is smooth, then this means that this is simply semi-stable. Otherwise, one needs to go to the normalizations of all the irreducible components and assume that they are semi-stable and assume that the fiber is reduced. So let us simply stick to the case where the fiber is smooth. It's much easier. So if we assume this, then this line bundle, the push forward of the discriminant is weakly positive. So this, well, can be somehow reformulated in terms of sections of multiple pools twisted by some ample line bundles and so on. But the modern definition of this weakly semi-positive, this being weakly semi-positive, is that this doesn't that a line bundle is weakly semi-positive at a point if this point does not belong to the restricted Bayes locus. I'm not going to define restricted Bayes locus, but this is what the result says. Unfortunately, this is not exactly what we wanted, because this weak semi-positivity depends only on the numerical equivalence class of this push forward. So it does not give any information in the pcar really, and there's not so much difference between this and the Bogomolov's inequality, except that now this works in the quasi-projective case, which is somehow strange. Okay, so I'm going to tell you a little bit what, unfortunately, one cannot hope that this result works in positive characteristic like that, although Morivaki managed to prove some version of this, assuming that ES is strongly semi-stable in positive characteristic. But even in characteristic 0, one cannot hope that we say the push forward of the discriminant is instead of weakly positive, for example, semi-ample. This would be something saying something really about the line bundle and not about numerical equivalence class. So unfortunately, this cannot work in general, but in some cases, one can hope for things like that. So one of the results that one can get is, say, for P1 bundles or for elliptic fibrations. So in this case, one can say that if we have a P1 bundle over some smooth variety S, not necessarily projective, if we have a rank R vector bundle, and if we assume that this is semi-stable at some point, then one can actually prove that 24 times the rank squared, the push forward of the discriminant, is already globally generated at the point S. So for elliptic fiber, and this works also in positive characteristic in exactly the same form. And there are also some results about elliptic fibrations, but I'm not going to talk about them. Instead, I will say something about what happens in case of products. And in the case of products, it becomes even more interesting for various reasons. So if we now have a product of a smooth variety with smooth projective curve in any characteristic, and if we take a locally free sheaf of O of C algebras, then if we have a vector bundle on the product, and if we have a family of A modules on this curve, which is parameterized by this S, then, and if we assume that this is semi-stable as an A module for some point, then one can actually prove that 12 times the push forward of the discriminant is global generated at a point. So I will not tell you anything about the proof of this result. I think, except that it is well, it uses some things like determinant line bundles, a little bit of Grothendieck manual formulas, and some generalizations of Falting's results on vector bundles on curves. So this is more or less what is needed to prove this kind of result. And it has some applications that, but maybe I don't want to talk too much about them. One of the things about this is that it generalized Bogomolov's inequality for some Higgs bundles on the product, and it works in any characteristic. And the second thing that I should mention is that it gives Bogomolov. So in case of when S is projective variety, then it gives Bogomolov's inequality on products and in particular, it gives Bogomolov's inequality on products of general curves. So this result was earlier proven by Hao Sun well, essentially 2 years ago. Okay, so now I'm going to go to some proofs of a little bit different things. So I would like to explain modern approach to Bogomolov's inequality. So I started with this inequality in case of one polarization, and then I mentioned that one can define slope semistability with respect to any collection of Neff divisors. And then this Bogomolov's inequality works in exactly the same way as written here. And then I would like to give a proof of this result, just because it's nowadays it's a pure fun to do that. And it's very easy. So we start with we can change the polarization D1 so that it becomes very ample, and then one can prove that this inequality is still equivalent to this inequality with this assumption. Then we can take a general pencil inside of this linear system associated to D1 and take the blow up along the base locus of this general pencil. This comes with a projection to P1 that I call P. So now the proof is by induction on N. And the induction assumption says that, well, the Bogomolov's inequality works on fibers of this P, which translates into saying that it works for polarizations that are of the form pi lower star of O of 1 from P1, then Q star D2 and Q star Dn minus 1. When we change polarization, then it implies the inequality for Q star D1 Dn minus 1, and then, well, the point is that if E is D1 Dn minus 1 semistable, then the pullback by Q of this E is slope Q star D1 Q star Dn minus 1 semistable, so we immediately get the inequality. So the only thing that I used here is that the Bogomolov's inequality for one polarization is true if I change the polarization at one point. And this is quite easy to prove by induction on the rank. So the basic advantage of this kind of proof is that it doesn't use any kind of Mehta-Ramanathan type theorems, and it implies a theorem of kind of restriction theorem of Bogomolov type. So I formulate a version that I proved. Well, the version of Bogomolov was with somewhat weaker constants, and then I proved the version of this also in positive characteristic. But when it used boundedness of semistable sheaves. So I don't want to use this. In characteristic 0, it really follows, and actually in any characteristic, it really follows from this Bogomolov type inequality. So, so now you see that this inequality says that if we, well, this theorem says that if we have a torsion-free sheaf which is slope semi-stable, then if we restrict to a general hypersurface of degree that is that can be effectively computed using the degree of the discriminant, then the restriction is still slope semi-stable. And this means that this inequality that we have here plus this result implies immediately a Mehta-Ramanathan restriction theorem without actually going into this result, at least in characteristic 0 at the moment. But in positive characteristic, it's also not so bad. So so here there is a result that goes back to Maruyama in characteristic 0 and also in the low rank cases. And then I proved it many years ago in arbitrary characteristic. So the result is the following. If we take a family of slope semi-stable sheaves with fixed numerical invariants, like the degrees of all the Chern classes, then this family is bounded. So they can be put into one large flat family of vector bundle parameterized by a scheme of finite type over our field, if we are in over a field. And now, well, now this result can be proven in a very simple way, namely in the following. I simply use induction on the dimension of the variety for which so I want to prove that the family of slope semi-stable sheaves is true. I want to assume that the family of slope semi-stable sheaves on varieties of dimension less than fixed number is bounded, and then I want to prove it in higher dimensions. So first, one uses exactly the same idea that I told you about in the case of Bogomolov's inequality in higher dimensions in over complex numbers. So this gives Bogomolov's inequality on the projective space. So let me go back here. This proof here really works in any characteristic on the projective space. I simply go from Pn to Pn minus 1. So this is what one gets here. And then when we have this one, then we can use it to prove the restriction theorem on Pn. This is exactly this result here. It depended only on Bogomolov's inequality. So we have this restriction theorem on the projective space. Then we use the induction assumption to get boundedness for slope semi-stable sheaves with fixed numerical invariants on the projective space. And then we proved this on the projective space. And then we simply use Never's normalization and reduce boundedness on any variety to boundedness on the projective space. So all of these steps are really standard, and they were known actually for ages, but the proof like that had to somehow wait. I don't know exactly why, but because somehow people realized that the most difficult case was the case of the projective space, and it was still not clear how to do that. And now with nowadays techniques, we have a very simple proof of this boundedness. This doesn't, fortunately, mean that my result from 2004 is obsolete, because I proved something much stronger than this one. So here we really proved the family of slope semistable sheaves, but with respect to one polarization is bounded, whereas the result that I proved at that time was somehow able to deal with multiple polarizations, and this is this cannot be proven so simply like this result. But at least this conjecture of Maruyama from 78 can be proven in a very simple way. So I think I will finish a little bit earlier, and thank you for listening.
Thank you, Adrian. Any questions?
Yeah, can you say that again? There was a story with simple monodromy. Can you show that again?
Okay, so the story with here, you mean?
1 second, I have to read.
So flat vector bundles with simple geometric monodromy should have torsion Chern classes.
But I mean, rank 1 is always simple, so I don't really understand.
What do you mean simple? It's never simple in the rank 1 case because you get GM, and GM is not simple group. It's a trivial group is simple.
What does that mean, simple? I don't understand.
Oh, it means that, well, so semi-simple group, it needs to be a semi-simple group, say, right? In particular.
Not reductive in general, but really simple.
Sorry?
Not just reductive.
Yeah. It's not just reductive. So it cannot be GLN, but SLN is fine.
Okay. And the other story is the SL2 story. When you
so the SL2 story here, yeah.
Contains SL2, so you have a complex point where you have SL2 monodromy, and then
or maybe GL2 monodromy, or maybe something that is of finite, that contains SL2 as a finite order subgroup.
Yes, and then the conclusion is assuming Bloch-Belinson, then you obtain the cycle here even on a fiber which is not defined over a number field. Is
yes.
that
Yeah. So here I don't, well, here I didn't assume that X is defined over a number field. X is any variety, but Bloch-Belinson is somehow needed to, actually I don't need the full strength of Bloch-Belinson. I need it only for some Shumura varieties.
no, rank 2? Yeah, okay. Okay, rank 2, it's okay. Yeah, thank you very much.
And is your S complete, or can it be affine?
Sorry, S?
Yes.
S can be anything. It's
Okay.
simply a reducible variety.
Okay, any other questions to Adrian? Okay, if not, let's thank Adrian again.
Thanks a lot.
Okay, thank you very much. Thank you, Adrian, and for great talk. And I upload the video of the talk in the evening today. Thank you. Bye. Bye.